Dear students, today we are going to see about the topics in metric spaces, the subject set theory and metric spaces. Definition of a metric space. Let M be any set. A metric for M, capital M is a function. So matrix is nothing but a function, row, with the domain M cross M, and the range is contained in closed 0, open infinity, such that row of x comma s is equal to 0 for any x belongs to M, and row of x comma y is always strictly greater than 0, where x is not equal to 0 for any x comma y belongs to M, and row of x comma y is equal to row of y comma x, and row of x comma y is less than or equal to row of x comma z plus row of z comma y, where x, y, z belongs to capital M. So what it explains? That means for any set M, we can define a metric as it satisfies the four conditions. A metric is nothing but that parameter can be compared to the real life distances. So just by measuring the distance from you to yourself is always 0. So without moving, we can measure the distance from ourselves, and that should be 0. That is row of x comma x is equal to 0. And for the distinct points x and y, so you are standing at one position, and from that you are just measure the distance from you to another person, then the distance is always strictly greater than 0. And the distance from x comma y, so distance between the first object and the second object, and the distance between the second object and the first object is also same. So there is no variation. And the last condition is the triangle inequality. The distance from x to y, so just measure the distance from x to y, which is always less than or equal to the distance from x to z and plus the distance from z to y. First you measure the distance from x to z, and then the distance from z to y. Just to take the sum, that sum value is always greater than or equal to the distance between x and y. So if the row satisfies the above four conditions, then row is the metric, and the distance does not negative. So we cannot say minus 6 kilometer, minus 5 centimeter. So it's always it's always positive. Therefore, the range is contained in closed 0 to infinity. Then the ordered pair, the set with metric, is called a metric space. These are all the examples. The first example is in R with a metric, absolute value. This one is absolute value metric. So consider the real number system. Now we define a function row as row of x comma y is equal to modulus of x minus y. This one is absolute value of x minus y. If the x minus y is negative, just by taking the modulus value we get the positive one for the set of all real numbers. And the notation for this metric space is R1 or R comma row. This metric is called the absolute value metric. So proof is very simple. For any element x comma y in R, the geometrical interpretation, modulus of x minus y is the distance from x to y. This one is a distance function. The distance between x comma x is always 0. You can easily understood. That is the distance from a point to itself is 0, and the distance between two distinct points is always positive. So here also we understood row of x comma y is strictly greater than 0. The next one is the row of x comma y is equal to row of y comma x. The distance from x to y is equal to the distance from y to x. The last one is a triangle inequality. Rho of x comma y is less than or equal to rho of x comma z plus rho of z comma y. So this is also we can easily prove. Next metric is the discrete metric. Here we consider the set of all real number R. Now we define another matrix. So here the metric is D from R cross R to the closed interval 0 to infinity by taking D of x comma x is equal to 0 for any x belongs to R. That means a point to itself the metric is 0, or otherwise the distance between for distinct points x and y is defined as 1 for any element x comma y and x is not equal to y. That is, the distance d of x comma y between any two distinct points is 1. The distance between the point to itself is also 0. So only there are two distances, 0 and 1 only. This metric is called the discrete metric and it is denoted by R suffix d. From these two examples, we consider the set of all real numbers as a set, but we can define two metric. So from this we can conclude that a given set may have more than one metric. Next definition is a cluster point of a given set. First you consider a metric space, let M comma rho, let A be a subset of M. The point A in M, so not belongs to A, need not belongs to A. So it should be M. So the point A belongs to M is called a cluster point of A in M if for every h is greater than 0, there exists a point x belongs to A such that 0 is strictly less than rho of x comma A is strictly less than h. So for any positive real number h, we can find a point x that is in A such that the distance between x and A is always less than that h. So for any h you can find out a point other than A. So that point x is in A. So if the condition is satisfied, then A is said to be a cluster point of A. That is, A is a cluster point of A if there are points of A distinct from A but arbitrarily near A. A need not be belongs to A. So I have already told you that. For example, you consider a metric space as R with absolute metric and let A is equal to 1 by 2, 1 by 2 square, 1 by 2 cube, like that, which is equal to the set of all 1 comma 1 by 2, 1 by 4, 1 by 8, etc. Here 0 is the only cluster point of A in M. So from the diagram, so if you choose any element in A and for any real number h, the distance between 0 and that element in A is always less than the positive real number h. Next one is the open ball in a metric space. Let M comma rho be a metric space and choose the element A belongs to M and radius R which is positive real number. Then the open ball B with the center A and radius R is defined to be the set of all elements, set of all points in M whose distance to A is less than R. So in symbol, you collect all the elements in M, the set of all x belongs to M, with the condition that rho of x comma A, that is the distance from x to A, is always less than R. In real life, you are at a room, just you take a radius R and around you draw a circle. So within a circle you collect all the things, then there is a open ball with the center consider as yourself. So we call B of A comma R the open ball of radius R and about A. For example, the open ball of radius 1 about the origin in the Euclidean 3 space is the set of all points x, y, z such that x square plus y square plus z square is strictly less than 1. So within a radius 1, you collect all the points that satisfying x square plus y square plus z square is which is less than 1. This means you collect all the points within a radius 1. next one, M is the closed interval 0, 1 with absolute value metric. The open ball with the center 1 by 4 and the radius 1 by 2 is the interval 0, 3 by 4. The here center is 1 by 4. So 1 by 4 minus 1 by 2 means minus 1 by 2. This is outside from the given set 0, 1. Therefore, the end point is 0. You consider the closed bracket 0. And the right hand side 1 by 4 plus 1 by 2 is 3 by 4. So, which is in the closed interval 0, 1. So, you consider the open interval 3, 4. The next example is the R with discrete metric. You choose any point in R with the discrete metric. Let it be A. Then, the open ball with the center A and radius 1 is equal to singleton A. And the open ball with the center A and radius which is less than 1, which is greater than or equal to 1, is the whole metric space. For example, B of A with the center A and radius 2 is equal to R with the discrete matrix. You get the whole matrix as a open ball. Next one is the open set in a metric space. Let M be a metric space. The subset G of M is an open subset of M. If every x belongs to G, there exists a number R is greater than 0 such that the entire open ball B with center X and radius R is contained in G. So, G is to be open. So, in that set, you consider any element X, and just by taking the center for the open ball as X, and you can find the one radius which satisfies. If you draw the open ball with the center X and that radius R, then the open ball must be lies in that set G. Then the set G is said to be open, or otherwise it should not be open. Example, you consider the plane R2. So in that R2, the set A of all points which is inside an ellipse. So in this ellipse, you can draw the you can take any point. So with the center that point, you can draw the circle which is lies in the ellipse. If P belongs to A, we can draw a circle with the center P which lies entirely inside the ellipse. The set B of our points inside the circle is an open ball which lies entirely in A. Therefore, A is open in R2. Next one is a limit point. Let E be a subset of a metric space M. A point X in M is called a limit point of E if there exists a sequence. So you can find out the sequence of points of E that converges to X. The set of all limit points, it is denoted by E bar, which is a closure of E. So X is a limit point, any point X of E is a limit point of E. That means every element of that set is satisfies the condition for the limit point. For the sequence x, x of points of E converges to X. So we can find a sequence which is a constant sequence. All the elements must be constant as X. So x, S that converges to X. Thus, if X belongs to E, then X belongs to the closure of E. So from that, we can deduce the corollary. If E is any subset of a metric space M, E is contained in the closure of E. These are all the examples. Let E denote the open interval 0, 1 considered as a subset of R1. Here 0 is a limit point of E. Because of you consider the sequence 1 by n that of points of E that converges to 0. But 0, a limit point of E does not lie in E. So the 0 need not be a point of the given set E. On the other hand, the closed interval 0, 1 does contain all its limit points. Every element of 0, 1, the closed interval 0, 1 is also the limit point of the given set 0, 1. So from this we can conclude the closed interval contains all its limit points. For a third example, if E is the set of all points x comma y in R2 such that x square plus y square is strictly less than 1, that is the interior of the circle of radius 1 with the center as origin, then the closure of E is the set of all points x comma y such that x square plus y square is less than or equal to 1. So if you find out the limit points for the inside of the interior of the circle, now then we get the closure is the points which lies in the interior of the circle and also the points lying in the boundary of the circle. This is because every point P1 such that x1 square plus y1 square is equal to 1 is also a limit point of E. The points which lies in the exterior of the circle is not a limit point of E. Next one is a closed set in a metric space. E be a subset of a metric space M. We say that E is a closed subset of M if E is equal to the closure of E. So from that we can deduce the result. X belongs to M is a limit point of the given set E is a subset of M if and only if there are points of E arbitrarily close to X. This one is the example. In R2 you consider a subset E, X is a limit point of E if and only if inside every circle about X there is a point of E. If L is a straight line in R2, then no point outside of L can be a limit point of L. Therefore L is a closed subset of R2. L contains all its limit points. Therefore L is a closed subset of R2. A plane in R3 is also a closed subset of R3. So outside the plane you cannot find out any limit point. For any metric space M, if X belongs to M, then singleton X is a closed subset of M. For the sequence of points in singleton X is the constant sequence x comma x comma x. So X itself is the only limit point of singleton X. So singleton X contains all its limit points, therefore it is closed. Thus if A belongs to R with the discrete metric, then the set singleton A is both open set and a closed set in R2. Thank you.